Stacy, where are you based out of?
I'm in Phoenix, Arizona.
Okay.
Yeah. We have a place over in Oregon, though.
Oh
And
yeah. What
yeah,
part?
it's a little town called Bandon.
Yeah, sure. I grew up in Oregon, so
Oh, well, we are very
yeah,
much
I
fans for
yeah.
no good reason, no family there.
Bandon's great. Yeah, I love Bandon. Oregon coast is really beautiful.
It is beautiful. We love it.
All right. Hello, everybody. Welcome to the CSINext September chapter program. I'm going to introduce to you your current chapter president, Ms. Stacy Sire, and I will turn it over to Stacy to get us started.
Hi, good morning, everybody. Happy September and welcome to a new season for CSI Next. So happy to have you here this morning. One thing that's a little bit different this year, if you've been tuning in with us for the past few years on our Zoom call, we have activated the chat session. So feel free to chat. I'd love to personally know where everybody is um, tuning in from. Since we are a virtual chapter, I've been very curious to know who is joining us and from where. So if you get a second, pop that in the chat. I'd love it. And then also, as usual, there's the way to give questions throughout there's the question and answer post. Feel free to post any of those and we'll get them in front of our speaker. And then after the presentation today, I'm going to make just a couple of announcements. And so stick around for some upcoming things that are exciting. But we know you have a lot going on, so thanks for being here. We don't want to waste any more time. Let's get it going. I suspect many of you are here because we all have wondered and needed to know how to keep air and water out of a building. And today is your lucky day. Today's presenter, I'd like to present Denali Jones. With his engineering background, he has spent his entire career focused on enclosures from high rises to hospitals, and he now serves as the technical director at ABAA, Air Barrier Association of America. Denali is a leading expert in air barrier systems and whole building air leakage testing. And yes, as he has admitted to me just a few moments ago, he's even helped write the standards and the testing that a lot of us use today. So we're really lucky to have him. So he's here to share deep knowledge and practical insights. And I have no doubt you'll walk away with something very practical that you can use on your buildings probably today. So please welcome Denali. Thanks for being here.
All right. Thanks, Stacy. That was a kind intro. Hopefully I can live up to it. But yeah, I'm going to be uh, doing essentially the same presentation that my colleague Ryan did at Skip a few months back. But this is all about whole building testing and kind of from a specifier or designer's point of view, what you guys need to understand about it, what it is, and how we deal with it. So how it, I'll just skip through the boring slides here. Essentially how it fits into the codes, energy codes, and some other green building programs, what that means for us now. And so we're going to talk about the current building code requirements, both on national and some local code requirements, as well as some eco-friendly building programs that are getting more and more popular these days. We're going to talk about what the air tightness test does, what it provides us, and how those results can actually be useful. We're going to talk about the different test methods that are available, and you'll see a number of different test methods. We're going to break down why they're important or why they're applicable in certain situations and not others. We're going to go through some sample language from a guide spec and talk about some of the pitfalls that I see in specs all the time, how to avoid those. And we'll talk a bit about some credentialing programs that you can specify that can help ensure that the people testing your buildings are qualified and know what they're doing. So we've got a lot of different supporting documents that the ABAA can provide you, including just things like this presentation. We're happy to deliver to local chapters or building enclosure councils or just even architecture firms. Education and outreach is a big part of what we do. So if you're interested, we've got lots of presentations available. We also have a whole building airtightness testing manual that actually is for sale. That's one of the few things that we provide that's not free, but it's a huge document that explains everything you need to know about whole building airtightness testing, and probably a lot that you don't need to know. It's hundreds of pages. It's essentially a textbook. On the left side here, we actually have hot off the presses two new guide specs, one for air barrier requirements, and then one spec that's specific to air barrier testing requirements. And so those were just approved by the board literally days ago. So they're actually, I don't think they're published on our website yet, but they will be very soon. And then the testing spec also includes a report template, which is that document with all the yellow highlights there. So we're trying to standardize the industry as much as possible. Everyone's testing the same way, everyone's reporting the same way, so we can compare apples to apples. That's a big goal of ours, is to make sure everybody's on the same page, doing the same thing and doing it right. So we've got a lot of different stuff we can provide that's helpful, both to specifiers, contractors, testers, you name it. We're a resource for the industry. But today we're going to talk about whole building airtightness testing. So we'll start kind of big picture with the national code requirements. So for a long time, it was really just this dichotomy of test methods here. So there's the material test, which is purely just testing the airtightness of a material, a single material. So either like a sheet membrane, or a foam panel, or even just a piece of sheathing. It's just the material. That's it. Nothing else there. And then the next step up would be the assembly test, where you actually test the air leakage through a 8x8 mock-up wall that's got penetrations, it's got fasteners, it has electrical outlets, it's got a fake window in it. So that's a bit more complicated, a bit more expensive. And then the system test, or the whole building test, is exactly what it sounds like. You test the entire building, as constructed. And so the codes, both IECC and ASHRAE, for a long time, this was kind of how they broke it down. You could either test the materials used for the air barrier and confirm they're airtight, or test all the assemblies used, make sure they're airtight, or test the whole building. Surprisingly, not a lot of people chose testing the whole building. You could imagine that is a fair bit more complicated and expensive to do than just testing a material or an assembly. So this is, some of the requirements here. This is from IECC. ASHRAE was really similar for a long time. The material test is ASTM E2178. The requirement to be an air barrier material is 0.004 CFM, that's cubic feet per minute, per square foot of the material, and that's at a pressure difference of 1.57 pounds per square foot. So they pressurize across that material. The ASTM test calls for a 1 meter by 1 meter sample, and they measure the leakage rate of air through that material. If it's less than 0.004 CFM per square foot, or it's 0.02 liters per second squared, then it's deemed acceptable by the code as an air barrier material. And that requirement's still in there. That's still in the code. And they provide a list of a bunch of different materials that meet that. That requirement, the 0.004, actually came from drywall. That's where we got these requirements from, is historically drywall was used as the air barrier on the interior side of the wall. They would just caulk all the penetrations and tape and mud all the drywall joints, and that was it. That was the air barrier. That's what people were doing. So when they were writing these code requirements, they just said, well, hey, let's just test a sheet of 1/2-inch drywall and see what the leakage is. And they did, and it was 0.004 CFM per square foot. That was the number they got. So they said, okay, anything that's at least as tight as drywall is good enough as an air barrier. And then the assembly test, that's ASTM E2357. that is 10 times more leakage you're allowed to have because there are penetrations, there are windows, there are board joints, things like that. So they're allowing you more leakage as an assembly than just a material, which makes sense. So it's 0.04 CFM per square foot, again at that same pressure of 1.57 pounds per square foot. And there's several assemblies they list that can comply with this. So CMU walls, if they're painted, can work. Stucco or plaster can work if it's at least a half-inch thick. There's several other examples as well. But and then the whole building test for a long time referenced ASTM E779, and we'll talk more about these standards later on here. But again, 10 times leakier was the allowable rate. They just figured, well, it's a whole building, it's a whole bunch of assemblies coming together. We're going to allow a bit more leakage. So they set that requirement at 0.4 CFM per square foot. And then later on in later editions of IECC and ASHRAE 90.1, ASTM E3158 was added as another acceptable option. So these are just excerpts from a table that we have in our manual, but you'll see that you know these apply as a option for compliance. So the code essentially says you have to have an air barrier, and how you demonstrate compliance is either testing the whole building or use all airtight materials or airtight assemblies. And there's that 0.4 CFM per square foot for both of those. But code requirements or testing requirements may come from more than one place. So you have to meet the code, whatever the code says in your jurisdiction. But then you also might have additional requirements from green programs such as Passive House, or LEED might have test requirements for whole building airtightness as well. Or there could just be an owner that wants an airtight building for one reason or another. A lot of institutional building owners tend to want higher performing buildings. So we see that in specs all the time where it's a hospital or a university or somebody that really cares about the performance and the durability of their building. They might specify something that's above and beyond code. So you may have test requirements that are kind of conflicting or one supersedes the other. So the code is just the bare minimum, and then you may have some other requirement on top of that that should be clearly defined in the spec. So let's talk about the national codes. So I'm going to focus mostly on the 2024 IECC, which is an updated version of the 2021 IECC. But 2021 is where a lot of things changed dramatically in terms of test requirements. But this is a little chart I put together, which is a bit hard to read and convoluted, so we're going to go through it in a bit more detail here. But essentially, there's actually 5 different compliance options. So the actual air barrier requirements didn't change. You still have to have a continuous air barrier. It's got to meet those material and assembly requirements. You have to seal everything up, but how you demonstrate compliance is what changed. And so it gives us 5 options, which I've got here on the right side. So the first 2 are really just test the whole building. But you'll notice option 1 is a different test standard than option 2. So and we'll talk about why that is. But they set the requirement now. They've dropped it from 0.4 CFM per square foot down to 0.35. So they've made it tighter. And the reason for that is we actually now have done enough testing of large buildings that we know 0.4 is really not hard to do. 0.4 is quite easy to achieve. And so we know we can do better and we can save energy doing it and get higher performing buildings. So they felt confident that we could meet that 0.35 threshold there. Option 3 is test a sampling of dwelling units. So this obviously it would only apply to buildings that have dwelling units. So dormitories, hotels, apartment buildings, things like that, condos. So you can test, instead of the whole building, just test 20% of the dwelling units. But you'll notice the tighter leakage requirement, 0.27 CFM per square foot. So you're not testing the whole building, but you have to get a better number for your 20% sample rate. And then option 4 is just testing portions of the building. So not testing the whole building, you're just testing parts of it, a representative sampling of the building. And there's specific language about which portions of the building have to be tested. You've got to test the ground floor and the top level, anything that's under a roof you have to test, and it's a certain percentage of all above grade wall area you have to hit. But you're allowed to test portions of a building, which really only makes sense for very large buildings where it's impractical to test the whole thing. And then the 5th option is not testing at all. It is a third-party design review and field inspections by a registered design professional. So you, in lieu of any sort of test requirements, you can have this option to just have someone else look at the drawings and inspect the building while it's being constructed. And one thing you may notice looking at this chart is that option 1 is always available, no matter what climate zone you're in, no matter how big the building is, you're always allowed to just test the whole thing. That is totally fine. Yeah, the other parts of this compliance path that you choose will depend on the size of the building, the occupancy type, and the climate zone. I didn't include it in this chart, but there's one exception. There are actually no air barrier requirements whatsoever for buildings in climate zone 2B, which is really just a small part of, I think it's Southwest Texas. There's not a ton of people there, but there's no requirement for anything in climate zone 2B in the 2024 IECC. All right, so if we break this down a little bit, let's look at smaller buildings. So you'll notice anything under 25,000 square feet, there is no distinction between climate zones. It doesn't matter what climate zone. And you'll also notice that option 5, the design review and field inspections, that is not an option in any of these scenarios. So essentially, if you're under 25,000 feet, you have to test. There's no exception around it. It's just you got to test. And what type of test you can do is really going to be any of the first 3 options, right? So test the whole building or test a percentage of dwelling units. And that's how they handle smaller buildings. So group I or R would be something with dwelling units. So that's multifamily apartments, residential buildings, and essentially anything that has a long-term sleeping unit, dwelling unit. So not like a hospital, but maybe a long-term care facility. And you'll notice, so option 2, that's testing the whole building per ASTM E779 or E1827. The reason that's allowed is these are smaller buildings, and we'll talk more about that in a later slide, but really for larger buildings, you don't want to be using those test standards. That's why option 1 is really the only option for larger buildings, which we'll see here. This is where option 2 goes away if we're above 25,000 square feet. So this is 25,000 square feet plus this slide here. So you'll see that colder climates are definitely more restrictive. And then once we get above 50,000 square feet, that's where partial building testing is allowed. So you're allowed to test, just a sampling of the building itself. And then this option 5, the design review and inspection. So omitting testing altogether, that's only available in warmer climates. So climate zones 0 to 4. 5 through 8, you have to do some kind of test. You cannot get out of it. So now, what do we do if the test fails? Well, there is what we call an oops clause. That's not what's written in the code, but this is the name that we've come up with for it. So if you're going with option 1, 2, or 4, basically, if you test and the result is greater than 0.35, which is the code requirement, so that's a fail, but it's less than 0.45, then you are required to, you're in this kind of in-between zone where it leaks bad, but not so bad that it's a total disaster. So you find leaks, and that's a different standard we'll talk about here in a little bit, ASTM E1186, how you would find the leaks, and then report the leaks and propose corrective actions to the code official and the building owner. And then that's it. There's no requirement. You're required to, I think it has language around, you're required to fix leaks that don't require tearing stuff off the building. So they won't make you pull cladding apart. They're not going to make you, reglaze windows or anything like that. But if it's kind of low-hanging fruit, just easy stuff that was missed that you can fix without destroying the building, you're required to fix that, but nothing else. You don't have to retest. You don't have to pass. You just have to report those leaks and fix the easy stuff, and that's it. And then if you're greater than 0.45, you do have to make repairs and retest until you're below that 0.45 threshold. So that's kind of the oops clause that's in the code. And then you'll see that that's not allowed for option 3. So if you're just testing dwelling units, a sampling of dwelling units, there is no oops clause. So this is maybe a little bit riskier because the actual language is for every unit that fails, you have to test 3 additional units. So if you're testing 20% of the units and a couple of units fail, well, now that's 6 more units you have to test. And if one of those 6 units fails, then you have to test another 3 units. So this can very quickly kind of spiral into testing every single unit in the building, which can get very expensive and take a lot of time. So this is something you really got to get right with sealing all those units so that you don't fail any the first time around. All right, so let's talk about ASHRAE. The ASHRAE 90.1 is actually simpler than IECC. You'll notice that option 3 and 4 are not part of ASHRAE 90.1. They have the same, essentially the same language around testing the whole building. If it is, and their threshold is 10,000 square feet, so it's even smaller. But essentially, if it's 10,000 square feet or less, you have to test the whole building. And they have a very similar oops clause. It's also 0.35 to 0.45 is that range. If it's greater than 10,000 square feet, you perform the whole building test, or you can do that option 5. And there's no distinction for climate zone or occupancy type. It's the same regardless. There are a couple other exceptions for semi-heated spaces in climate zone 0 to 6. Don't need to do anything. And then single wide CMU buildings only in climate zone 2B, you don't need to do anything. Some kind of weird legacy exceptions in there, but that's kind of the way ASHRAE 90.1 breaks down. So let's talk a bit about local jurisdictions. This is where it gets really complicated because so many different jurisdictions take either IECC or ASHRAE 90.1 and modify it or do their own thing with it. So one example is where I live. I'm in Seattle. So Seattle, actually, there's first of all, there's the Washington State Energy Code, which is based on IECC. They took that code and made it more stringent. And then the city of Seattle actually took that and adds additional language around it as well. So there's so many different variations of this throughout the country. So a failure in Washington State. This is from the 20. This is I think this is the 2015 code. It's a little different now. But essentially, if leakage exceeds 0.4, then you have to repair and retest, right? Which is above and beyond what the code, the national code says. And if it's between 0.25 and 0.4, that's sort of the oops clause there that comes into play for Washington State. So this is a big deal to know what's required in your local jurisdiction. I don't know if we have any Californians in the chat. I haven't looked yet. But California has their own climate zones because they're special, and they've got requirements in certain climate zones and not others for testing and retesting if it's a failure. Fort Collins is another example of a local jurisdiction that has a pretty strict air barrier requirement that the rest of Colorado does not. So, and then in the California State Energy Code, if you fail the test, there basically isn't any consequence. You just have to report that you failed. There isn't like you don't have to repair, or at least that was true back in 2019. But Fort Collins, however, they have no oops clause. If you fail, you fix it and retest and keep retesting until you meet it. So very different scenarios for doing the same type of testing. So this is why I get asked frequently, hey, what are the code requirements, in, I don't know, Cincinnati or Phoenix or whatever, and I always have to say, well, I don't actually know that because there's so many different variations of this in local jurisdictions that I'd have to spend the time to look it up. So you got to know the code in your local jurisdiction. Utah is another one that has requirements for some buildings and not others, and it's different for residential versus non-residential. New York State also, or sorry, New York City has requirements as well. And so lots of different ways that you can test, and also what happens if you fail is going to be different in a lot of cases. Green building programs are two of the big ones, Passive House and LEED. You'll notice, so the current IECC requirement was 0.35 CFM per square foot. Passive House, which is kind of the gold standard for airtightness, is 0.08 CFM per square foot. So way tighter than the code minimum. Just to give you some perspective on what a really tight building is, that would be Passive House. LEED also has some requirements for various points that you can get. And the consequence of failure for these is pretty cut and dried. If you don't meet the Passive House requirement for airtightness, you don't get certified as a Passive House project. If you're going for LEED points and you don't meet the airtightness goal, you don't get those LEED points. Period. There's no oops clause. There's nothing like that. It's just you have to meet those requirements, or you don't comply with the green building program. The Army Corps of Engineers has been doing airtight buildings for a very long time, which then kind of bled over into the GSA for any federal government building. They have different tiers they can meet. And those are both pretty strict. If you don't meet those, you have to repair and retest. And let's talk about the different test methods. All right, so I've talked about a lot of different ASTM standards here. There are many more. I don't want to get too far into the weeds on this, so I'm going to try and keep it high level. This table is from our big air leakage testing manual. So you'll notice that some things are kind of universally true for all test standards. Like interior doors are going to be propped open. Exterior doors and windows are going to be closed and latched. You know, openings that are not intended for ventilation, like, you know, plumbing traps, floor drains, things like that. Those all need to be isolated for the test. But otherwise, there's quite a range of difference between how the testing is done and what is done to the building prior to testing. Oh, this is another one that's really important. So pressure uniformity is going to be essentially the same or very similar for a lot of these test standards, and we'll talk about why that is here. But let's first get into the basics of what whole building testing is. So in the simplest version of this possible, you can just think about if you've got a fixed volume, which is your building, any flow that you put into the building, air that you pump in, it has to equal the flow out of the building, assuming the pressure in the building is constant. Right? So if you've got a constant volume, constant pressure, flow in equals flow out, that's conservation of mass. That's how that works. So our flow in could be through the blower door, which is just a big fan. Our flow out is the leaks, right? So we're trying to measure the leakage of the whole building. So we close all the windows and doors, seal everything up, and blow air in through the fans. And then we're assuming that that flow out is going to be the same as the flow in. So that's kind of a funky thing, is that you're not actually measuring airflow through the leaks, you're measuring airflow through the fans, and then assuming that it's the same as the air out through the leaks. So where it gets complicated is as the building gets bigger, you can't just have one fan blowing air in. You need a bunch of fans. You need a lot more volume of air, more than one fan can do. So you've got to link all those fans together. You have to measure pressure in a whole bunch of different places and control everything all simultaneously. That's where this gets tricky. But conceptually, that's all you're doing, is you're blowing a bunch of air in, measuring it, and equating that to flow going out through the leaks. The reason you have to measure a bunch of pressures is you want to make sure you actually are getting the same pressure throughout the whole building. So we call that pressure uniformity. So if we've got a 10-story building and we've got a bunch of fans on level 1, we want to make sure we're actually getting the same pressure on level 1 as we are on level 10. So the air is actually reaching every part of that exterior envelope. And actually the way that these fans work is it's a bit of a misnomer to say we're measuring airflow. We're not actually measuring airflow, we're measuring pressure. And so the fans have openings on the inlet side of the fan, and so we are sucking air through that opening. We know how big that opening is because it's been calibrated to a specific size and shape. And so we measure the suction pressure, it's called the fan pressure, through the fan across that inlet. And then we know what the flow is through that opening because we know the size and shape of it, and we know the pressure across it. So it's all just measuring pressures, really. But we can quite accurately determine how much flow is going through each fan, add that all together, and then we get our leakage rate. All right. So this gets difficult in a number of different ways. Very tall buildings or very large indoor-outdoor temperature differences that can make things difficult. So if it's really cold outside and warm in the building, that's tricky. Lots of wind or highly variable wind can make things tricky when you're trying to measure stable pressures. Buildings with multiple zones, I'll talk about why that's tough. And leaky buildings are just harder to test in general. And multifamily buildings, and I'll talk about why that is too in a second here. So the first one is these first two are kind of one and the same. So very tall buildings or very large indoor-outdoor temperature differences. This is due to the stack effect. So stack effect is really just the fact that warm air is less dense than cold air. So the warm air will rise to the top of the building. It's going to try to force its way out, which is going to draw cold air in at the bottom. So you get we call a positive stack pressure at the top. So it's going to be pushing out, and you get a negative stack pressure at the bottom. This is also sometimes called the chimney effect. This is how chimneys work. But this can be difficult in tall buildings because it's actually proportional to the height of the building, and also the temperature difference. Those are the two things that make the stack pressure bigger. So taller building, more stack, bigger indoor-outdoor temperature difference, bigger stack. And your fans basically need to overcome this stack effect. And so the bigger this is, the harder it is to overcome. And this, again, this is only a severe limitation in very cold climates or in very tall buildings. I'm talking like 30, 40 stories plus. That's when it can start to get tricky. So this is a pretty small subset of buildings where this is really a big factor. But it is something to know about if you're working on a high-rise building in Chicago and it's going to be tested in January. That could be an issue. That could be something that you might consider doing, just testing portions of the building and not the whole building. But ASTM E3158 will get around a lot of these issues, and we'll talk more about that here in a second. But this is one of the reasons why some of these other test standards like ASTM E779 are not really appropriate for tall buildings. They're not meant to deal with large stack pressures. Wind is the next one. Fairly obvious why this is a problem. You're trying to get stable pressure readings, both indoors and outdoors. That's hard to do if it's a really windy day. So this can make testing quite challenging. Multiple zones can be difficult, and this is really just logistically challenging, just from the testing point of view. You've got to make sure if you're testing the whole building, but it's chopped up into different sections, you have to simultaneously pressurize those sections and get them to the same pressure all at once. So that's difficult to do. Sometimes this is just inevitable and you have to do this with just the way that the construction sequencing goes. But this makes it challenging. Leaky buildings and multifamily buildings are kind of lumped together because they are one and the same a lot of the time. Multifamily is leaky just because you've got a ton of different penetrations, exhaust penetrations. So you've got all these different, range vents, you've got bathroom vents, you've got dryer vents, usually something like 4 exhaust fans per unit. You got, your stove, your bathroom fan, your dryer, and then usually another whole house ventilation fan somewhere. So the goal of the test is to measure leakage through the air barrier, not measure leakage through the HVAC systems. So it's trying to figure out how well put together are all of the sealant joints, the tapes, the membranes, all that stuff, not like how much flow goes through your ductwork. That's kind of a different concern. So trying to isolate these exhaust fans for the test is very difficult and time consuming, and also often ineffective. These infrared shots here, these are from real tests that were done where these exhaust fans were taped on the interior, but you can see how much these are just lighting up. That's all the warm air in the building just dumping out of these exhaust fans because they weren't taped perfectly. So it's really hard to get these totally isolated. And as a result, multifamily buildings often appear leakier than they really are. All right. So let's talk about multi-point testing. So this is what we're actually doing when we're getting data. We're measuring pressure measuring flow at multiple different pressures. And this allows us to develop a characteristic flow curve for the building, so we can actually tell you what the leakage rate is at any pressure. So we're reporting the leakage at 75 pascals or 1.57 pounds per square foot. That's what the code requires for reporting, but we're actually testing at a bunch of different pressures. And really the biggest reason for this is so you don't get something like this. So this is the left is a graph of what I would call good data, and you can see it forms a nice smooth line with pressure on the x-axis and the flow rate on the y-axis. The picture on the right, this is what it looks like when something opens up during the test. So this would be like a door that wasn't latched that just blows open. So you can see there's that big jump in that curve. So that's pretty clearly something went wrong there. And this would throw up a lot of red flags in the testing software that, you got to go check this out. But if you were just to test at 75 pascals, just crank your fans on and just get a number, you wouldn't know this is happening. You have no idea because you only have one data point, so you don't really know how good that data point is. You don't have that smooth line to tell you that the building is holding steady and nothing's blowing open. And this kind of stuff happens a lot. I would say probably more often than not, you'll see something blow open during a test. On a big building, there's going to be some window that wasn't latched somewhere, some door that was left unlatched, or some bit of masking that wasn't done very well that just fell off. You'll see stuff like this all the time, and so this is why that multi-point test is really important. So ASTM E779, this is one of the multi-point test methods. It was kind of the gold standard for a long time. It was the only thing that was around. It was developed in the 80s, and it was really written for testing single-family homes. Nobody was testing large buildings back then, and it's if you read through this carefully, it's got really strict limitations on weather conditions. It requires testing at really low pressures. So if you're trying to get a stable reading at a low pressure, things like stack effect and wind are really, really difficult and prohibiting to test at. And you'll see it offers very little guidance on how to actually prepare the building. I mean, it talks about stuff like closing the chimney flue, and it's very clearly written for testing a house. It has no guidance on what do you do with a DOAS system on the roof or elevator pressurization fan. Like, it's not written for those types of buildings. So a lot of the guidance on how to prepare the building is very limited and kind of left up to the tester's interpretation. And it also actually only requires taking 5 data points, so flow at 5 different pressures. 1827, this was also referenced in the code. This was developed in the 90s, again, just for single-family homes. It does have a bit more guidance on building prep, but very little on equipment setup. It's really meant for just assuming you're just testing with one fan. It also requires testing at very low pressures. And this is not a multi-point test. It's got 2 different options. One is a single point and the other is a 2-point test. So 2 is not a lot of data points to define that line. So this, both E779 and 1827, I would say are still fine for testing small buildings, which is why that in the code, that option is for buildings that are under, I think, 10,000 square feet. That's fine. You can test a small building if you've got good weather, but again, the weather windows are small with these tests. This is what we really should be striving for. So ASTM E3840x2160, this is the one that I helped develop. This kind of combines parts of E779 and E1827. It was developed specifically for large and complicated buildings. It offers extensive setup guidance and building prep guidance. It requires testing at much higher pressures over longer time intervals to accommodate bad weather. So you can overcome quite a bit of stack effect and wind by just using this test standard. And it's also the only test standard that actually underwent round robin repeatability testing. So there was a study that was done, it was an ASHRAE study when this was first developed, where a bunch of different teams went out and tested the same building with different equipment on different days, different people setting up the equipment and building, just following this test standard and seeing how close the results were. They were all very close. I don't remember the number, but this is the only test standard that's done that. So this is really what we should be striving for. All right. So how do we specify ASTM E3158? Well, there's 4 things that you need to actually have in the spec. The first is a reference pressure. So this is the pressure that results are reported at. Typically, this is going to be 75 pascals. That's what the codes reference. But that's, this is up to the specifier to write this into the spec. So the reference pressure, usually going to be 75 pascals. It also allows you to test pressurization or depressurization or both. So this is the directions the fans blow into or out of the building. We recommend both. In most scenarios, that's going to give you more accurate results. But there may be some odd scenarios where one might be more appropriate than the other. A situation I've run into is testing an addition to an existing hospital, where the existing hospital was operational during the tests, and so they were very concerned about blowing contaminants into that hospital. So we just depressurized. We did not pressurize. So there's kind of oddball situations like that, but this is something that needs to be specified. Which direction are you testing, or are you doing both directions? The other one is how the building is configured. So there's 2 different options. So there's an operational test or an envelope test. And so an envelope test is where all intentional openings, so basically all HVAC systems, are sealed. So with tape and plastic sealed off, you're trying to isolate them so that the leakage through them is 0 or as close to 0 as you can. And that's going to test just the air barrier itself, not the flow through the HVAC systems. Operational test is essentially configured as close to normal operating conditions as possible. So you don't really seal anything. You would shut off mechanical systems and close dampers, but that's it. So if there's a exhaust fan with no damper, it would just be left wide open. We're actually writing a guidance document right now about why you might use one or the other, but generally for code compliance testing, you should always be doing building envelope. That's not written specifically in the code, but that 0.35 requirement, that's kind of assuming you're going to be sealing up intentional openings. If you try to do an operational test for code compliance, you'll quickly find out that you're going to get a lot more leakage and you're going to have a lot harder time passing. And then 3158 also has 3 different procedures in it. It has the multi-point procedure, which we've talked about, that actually requires 10 different data points, so flow at 10 different pressures. It also has a 2-point and single point, which is really just a carryover from E1827. And I would not recommend doing that unless the building is very small or you have absolutely perfect weather conditions. All right. So let's see. Gotta speed up here. Just realized what time it is. So we've got spec language here. Again, these are just some notes that were added into our spec that's going to be published very soon. But you need to specify operational or envelope. You need to say the test mode, both pressurization and depressurization, or one or the other if applicable. And then you'd include the multi-point procedure, test method. And then you also have to specify the maximum air leakage rate. So either, 0.35 or whatever the requirement is that you're trying to hit. I'll quickly go through part one of this spec. We do have language in there for accredited testing agency qualifications. So ABAA does actually offer an ISO 17024 accredited training and certification program for teaching people how to do this. It's a very extensive course. We developed it with support from the blower door manufacturers. And we have a certification program that goes with it, which we would definitely recommend specifying. We've got many people certified now in this, and we're trying to get the industry kind of up to speed on how to test large, complicated buildings. So we developed this credentialing program. It's a full week-long training course, and you can include that in your specifications. We also have language in here about what to do if the test fails, contractor responsibilities at that point, and how to identify those leaks. So I don't have a ton of time left here, but how do we actually find air leaks? You can't see air with your eyes, so you need to figure out other ways to actually identify it. There's a bunch of methods, but the two that are most commonly used are infrared thermography and smoke. So smoke is pretty simple. It's just a way to visualize airflow. So if you've got the building pressurized and you put smoke near a leak, that smoke will get blown out through the leak and you can actually see it. Or if you've got the building depressurized, you can smoke from the outside. It will suck air in, and you'll see the smoke move. I believe this is, hopefully this will play here. So this is just some examples of smoke testing. You can see this is a pretty bad, leakage rate on this building. But yeah, this is all smoke pouring out with the building under pressure. So it's a way to visually identify air leakage pathways, because you can't, this air is flowing out all the time, but you can't see it unless there's a visual cue here. All right, so a lot of these are from forensic investigations of existing buildings that were having lots of problems. So of course the leaks are going to be pretty dramatic, but you can do this on new buildings as well. Infrared thermography is again just a visual tool. You'll see air that's a different temperature that's flowing over these surfaces, and it will highlight them. But that's a whole different training course on infrared thermography in buildings. But yeah, I'll wrap this up here. It's whole building airtightness is going to become more and more required in the future. It's really important to understand all these test methods are not the same. There are big differences in how they should be applied. And we're going to give you this spec here very soon. It's going to be on the website. That it will make this presentation very short. You just need to make those 3 or 4 decisions about reference pressure, test method, and test direction, and etc. But the test itself is actually quite complicated. Getting good data, good, reliable, accurate data is not easy. Setting up the building is not easy. Setting up the test equipment is not easy. This is why we developed this training course, and really having these qualifications and expertise is very important. And really we want to stress that. There is some language now in ASHRAE and IECC talking about qualified testing agencies. They don't specifically require our training, but we want to make sure that the people doing this kind of testing actually know what they're doing. All right, so that's all I got, and happy to answer questions.
Denali, I think we've answered everything we had in the Q&A portal.
Okay.
And again, as this was, for those who were at Skip earlier, this was an excellent presentation. good refresher, at least from my end. So from the Q&A side, Stacy, I think we're all wrapped up, and I will let you take it from here.
Oh,
You're on
muted.
mute, Stacy.
I am on mute. Thank you. Sorry about that. I was just going to say that everybody on this presentation would be interested in this because there's nobody here, according to the attendees that said where they're from, that's in Zone 2B. So there's nobody
Okay.
in
Yeah.
Southwestern Texas. So all of us are very interested and very much need your information. So I am assuming that we will be sending out this PDF, and it's going to have this same information here on that. So
Yep.
they'll know how to get a hold of you. That is absolutely perfect. Thank you. We cannot thank you enough. I don't know how your brain. I thought that I liked Gantt charts and spreadsheets a lot, but I think that I've met my match here with somebody that likes them even more than I do. So thank you.
There's a lot to keep track of, and I certainly don't have all of it memorized.
Well, it's a lot. You're right. So we appreciate having you as a resource to fall back on these requirements that we have. So thank you. And for the rest of you that are on the line still, some upcoming things. If you notice the message that I sent out or on our website that we are going to be meeting on Wednesdays now, unless otherwise noted. There's always that little, asterisk, unless otherwise noted. October is a ... asterisk noted because our program next month is very different, and we've had this scheduled since late spring, which was before we got our new date set. So next month for October, October the 10th, we will be having a great topic called Building Diplomacy, presented by James Timberlake, and he's going to walk us through his firm's winning of an international design competition for the United Kingdom and the embassy, the U.S. Embassy in the United Kingdom in London. So it's going to be a great opportunity to take a peek behind the veil of his walk from winning a design competition through construction. So join us for that. Also, keep an eye on the website for our CDT boot camp with Dean Bortz, one of our members, and that's coming up. I don't remember the exact date, so take a look at the website.
October 25th.
October 25th. Thank you, Mark.
From 9 a.m. to 4 p.m. Eastern.
There you go. Okay, and it should be on the website already, so take a look at that. And then I've already been getting inquiries about, are we going to do our December CEU targeted date again, kind of what we call the procrastinator session. And yes, we will. So that date, I don't think has been set yet, but that will be coming soon. So keep your eyes on our website for upcoming events. And thank you for joining us today, and we will see you next month.